Now we can prove the work-kinetic energy theorem for work done by a constant force by using the kinematic equations for a constant acceleration and Newton's second law. We'll do a mathematical style proof. So suppose that a constant force F is applied to a particle or non-rotating rigid object of mass m, then by Newton's second law, we have that the force causes the particle or object to accelerate according to the equation force is equal to the mass times the acceleration of the particle or object. Now, once we choose a reference frame that corresponds to three-dimensional space, we can decompose the force vector into its components. And so the force F is equal to the mass times the quantity, a sub x times I hat, where a sub x is the component of the acceleration that is parallel to the x-axis, plus a sub y times j hat, plus a sub z times k hat. And we can also decompose the displacement vector. So we have the change in the x-coordinate times I hat, plus the change in the y-coordinate times j hat, plus the change in the z-coordinate times k hat. And so the work done by the constant force F is the dot product of the force with the displacement vector. So we have the mass times the quantity, a sub x times delta x, plus a sub y times delta y, plus a sub z times delta z. Now for motion in one dimension, and say for example the x dimension, that is the dimension corresponding to the x-axis in our reference frame, under a constant acceleration, the difference of squares of the final speed and the initial speed is equal to 2 times the acceleration times the displacement. And so we have that a sub x times delta x is equal to 1/2 the quantity, the difference of squares of the final speed and the initial speed. And similarly, a sub y times delta y is 1/2 the quantity, the difference of squares of the final speed and the initial speed, and a sub z times delta z is 1/2 the final speed squared minus the initial speed squared. And so the work is equal to 1/2 the mass times the quantity, v sub x final squared minus v sub x initial squared, plus v sub y final squared minus v sub y initial squared, plus v sub z final squared minus v sub z initial squared. We can regroup the terms so that we have 1/2 the mass times the quantity v sub x final squared plus v sub y final squared plus v sub z final squared minus the quantity v sub x initial squared plus v sub y initial squared plus v sub z initial squared. Now the square of the final speed is the square of the magnitude of the final velocity, which is v sub x final squared plus v sub y final squared plus v sub z final squared. And similarly, the square of the initial speed is v sub x initial squared plus v sub y initial squared plus v sub z initial squared. And so the work is equal to 1/2 the mass times the difference of squares of the final speed and the initial speed, which is 1/2 the mass times the final speed squared minus 1/2 the mass times the initial speed squared, which is the final kinetic energy minus the initial kinetic energy. Now that we know that the work-kinetic energy theorem is valid for work done by a constant force on a particle or non-rotating rigid object, let's use it to solve a problem. Suppose the wagon from the previous examples has a mass of 15.0 kilograms. What is its speed after the 3.00 meter displacement if the wagon was initially at rest? So recall from the previous examples that the work done on the wagon is 130 joules. We now know that the mass of the wagon is 15.0 kilograms and that the initial speed is 0 meters per second. Using the work energy theorem, we have that the work is equal to 1/2 the mass times the quantity, the final speed squared minus the initial speed squared, where the initial speed is 0. And so we have that the work is equal to 1/2 the mass times the square of the final speed. So the final speed squared is 2 times the work divided by the mass, so that the final speed is the square root of 2 times the work divided by the mass. So this is the square root of 2 times 130 joules divided by 15.0 kilograms, which to 3 significant figures is 4.16 meters per second. Notice that if the particle or object was initially at rest, then the work is equal to the final kinetic energy of that particle or object. And this gives us a physical interpretation of kinetic energy. The kinetic energy of a particle or non-rotating rigid object is equal to the work required to accelerate it from rest to its current speed. And if the particle or object is brought to rest, then the work is equal to the negative of its initial kinetic energy. Equivalently, the initial kinetic energy is equal to the negative of the work done on the particle or object. That is, energy is transferred out of the system consisting of the particle or object. And this gives us a second interpretation of kinetic energy. The kinetic energy of a particle or non-rotating rigid object is equal to the work it can do in the process of being brought to rest. So let's look at another example. A soccer ball with mass 0.420 kilograms is initially moving with speed 2.00 meters per second. A soccer player kicks the ball, exerting a constant force of magnitude 40.0 newtons in the same direction as the ball's motion. Over what distance must the player's foot be in contact with the ball to increase the ball's speed to 6.00 meters per second? Okay, so in this case, the applied force is in the same direction as the displacement. So we have that the work is equal to the magnitude of the force times the magnitude of the displacement. This is also equal to 1/2 the mass times the difference of squares of the final speed and the initial speed. And so we have that the displacement is equal to the mass times the difference of squares of the initial speed and the final speed divided by 2 times the magnitude of the force. And so this is 0.420 kilograms times the quantity, 6.00 meters per second squared, minus 2.00 meters per second squared, divided by 2 times 40.0 newtons, which to 3 significant figures is 0.168 meters. So as a second exercise, if the opposing force of friction on the soccer ball from the previous example is 1.40 newtons, how far will the ball travel before coming to rest, assuming no other interaction with the ball? Okay, so in this lecture we have begun to look at the concept of energy, and we have seen how it can be applied to real-world problems using the system boundary environment model. In particular, we have looked at how the energy model can be applied to mechanical systems, and we have seen that work is a mechanism that transfers energy into or out of a system. We have also looked at one type of energy that an object may possess, the kinetic energy, the energy due to its motion. And the Work-Kinetic energy theorem has given us a physical interpretation of kinetic energy. Kinetic energy is equal to the work required to accelerate an object from rest to its current speed, and is also equal to the work an object can do in the process of bringing it to rest. The important equations from this lecture are the following. Work is equal to the magnitude of the force times the magnitude of the displacement times the cosine of theta, where theta is the angle between the force and displacement vectors. This is equivalent to the dot product of the force and displacement vectors. The kinetic energy of an object or particle is 1/2 its mass times the square of its speed, and the work is equal to the change in kinetic energy. The first 3 of these equations are operational definitions, and the last is the Work-Kinetic energy theorem. Next time, we will look at another type of energy that an object may possess, potential energy, and we'll also look at conservative versus non-conservative forces. So I hope you have enjoyed the first lecture. Thanks for watching.